So in this last of the videos for this week, we're going to talk about logging. So beyond just software practices, which are typically followed by experienced software engineers, let's take a look at what makes machine learning applications a bit more nuanced for certain types of, information. And therefore, if you spend the time to make sure that those types of information are logged correctly and at appropriate places, then it saves a lot of headache for you when the model is finally going to production. So this set of slides are meant for the data scientists themselves because they are the ones who are writing the code. But obviously, if you're going to take somebody else's code and operationalize it, then you can also do some of this activity. So what constitutes clean log design from the perspective of ML? There are three aspects to it. The first is it needs to be consistent in format. So the example here is because most logging tools are part of the observability stack, which is modern, JSON as a mechanism of encoding information is something that is preferred. And this makes it very easy for most of these observability tools to pick up information and then index that information for various use cases like searching and things like that. So structured JSON and following a consistent format for that structured JSON is something that's highly preferred. Then have minimal amount of raw data, right? So not full images, not the exact copies of raw data directly. Have it in a way that's minimal. This makes for vastly lesser sized logs. So the alternative is you log every single request that comes in, and that will really balloon up the extent of log space that you end up using. In fact, you'll find that in most public cloud deployments in production, the logging infrastructure or the observability infrastructure is the one that actually costs the most amount of money, at times even more than the actual data processing or the functionality processing parts of the cloud platform. So that's mainly because there's a lot of resource utilization that observability, logging, all of that uses behind the scenes. So if you minimize the extent of load that you put on that system, you will also therefore proportionately reduce the cost that you might incur on it. Now, there are two gotchas here, right? One is the fact that raw data is anyway going to be frowned upon in many scenarios because it leaks privacy information. So let's say, for instance, you're operating in a regulated environment and the set of production workloads that you see are related to people's KYC information like Aadhaar card, addresses, etc. And the machine learning model is predicting, for instance, whether a person is going to be a fraudulent candidate or not based on this personally identifiable information. As per the Data Privacy Act that's enacted by the government as well of India, without consent, you should not be processing this data. And even with consent, even if you process this data, it should not be used or visible to other players in the ecosystem to whom that consent is not being given explicitly by that end user. How do you prove these things? You prove by having traceability of the data and access logs for all the different ways in which the data can be accessed. So typically that kind of control is exercised by having the data be residing in a database and have strict controls over the database. But if you start logging raw data, right, the raw data that comes into the fraud model, and you start logging that information, the logs are not under the purview of the database. They are part of the observability stack. And typically the team that accesses the observability logs are not the business teams, are not the fraud control teams. They're actually IT teams. And the IT teams are now having access to customer PII information, right? Because you've embedded those in the logs directly. That's a leakage. And that leakage will be frowned upon under those scenarios. Now, there is a separate set of concepts and I think we spoke about that earlier in the MLOps course, where because it's a regulated environment, you're expected to provide traceability for every single customer request that's coming to you, because you need to prove that you're not biased against that particular customer at a later point in time. So example is, somebody's applied for a credit card or a loan. You've rejected the loan based on genuine parameters because you think it's risky to lend to that individual. Let's say the individual makes a complaint at a later point in time, like 2 years from now, stating that this particular bank has discriminated against me, and therefore I'm filing a complaint. At that point, the regulator can come to you and say, hey, show me how you decided that this particular individual is not eligible for a loan, which means they're effectively asking you to trace all the input data elements that were given to the model, the output of the model itself, and then explain to the regulator that these are genuine executions. So what they're asking for is the trace of the exact data set itself. You might not have, obviously you should not be logging it in the logging infrastructure, but there's a separate database meant for these kinds of purposes. Usually those are audit databases under the purview of the audit team, not in the IT team, not in the data science team. So keep these things in mind when you start logging data itself of the model that's being given, or rather the data that's being given to the model. The third angle of logging is tag as much information as possible, especially things like traces, right? So what's a trace ID for a machine learning model? It's basically a specific invocation. So if you cannot log PII information, or rather it's a best practice not to log PII information, how do you create a trace ID? You let the system create the trace ID automatically, right? And then you link the trace ID back to the various source systems that it came from, the microservices that it goes through behind the scenes, the models that it executes on, so that you have one consistent way to trace that particular request end to end. And that gives you the information that you might need to debug a particular problem. So you can also obviously tag the model version, whether you're using the champion model or the challenger model, tag the request ID, etc., etc. So let's take an example. Obviously, the basic level of logging that we all get to do as part of software engineering is, use the logging framework that's there in every language, Java, Python, Node, etc. So here, I import the logging and then say that only info level logging needs to be logged. Info level logging means anything above info will also get logged automatically. So info, error, and then severe errors as well. But lesser than info would be things like debug logs. That's not going to be logged. So that's what this configuration means. The good part is that by default, if you execute this in Kubernetes, this kind of logging information is getting collected by Google Cloud's cloud logging feature. You don't need to do anything special beyond just making sure that the logging instrumentation is there in your code. Now, when we say structured JSON is a consistent way to log information, this is what it means, right? So wherever you have matrices, especially numerical values that you want to log, like for instance, the extent of data that's been processed successfully, the percentage completion, latency information, average, etc. You think about a structure of how you want to represent the data, and then produce that output as a structured JSON and then log that information. So that becomes very easy for you to search at a later point in time. What about errors, right? Obviously, the errors which are captured are the errors that are useful. If the error is not captured, then that can result in catastrophic impact, right? The good scenario is that the Google Cloud platform itself, captures that error and it's there somewhere in a big stack trace, and then you got to go hunt for it. But the even better thing is to actually, handle the errors yourself. Errors are going to be common, right? Most production systems need to deal with different corner cases of how data comes in, of how models behave, etc. So deal with the exceptions yourself and then provide graceful behaviors for it. So add exception handling in the code, and this also enables traceback. So the Google Cloud error reporting works out pretty well out of the box with most languages out there, Python, Node, etc. So all you've got to do is basically, make sure that you've got a try catch block. Or in Python, it's try except block, and make sure that the exceptions are caught there, and the appropriate information is also fed to it. And then for errors that occur frequently, the cloud error reporting will actually provide useful summaries of what those errors are, so that it's something that you can act upon at a glance. Tracing is a very useful activity that's available for being able to look at what happened to one specific request. So the way you would go about tracing for things like latency or understanding where a specific request got dropped is to use something called as a trace span. The trace span is a concept that allows you to create a trace ID and then propagate that across your log information and propagate that across your microservices that are handing off to each other using APIs. So you propagate the trace context across the pods, and then you also annotate the logs so that subsequently you can correlate all of this together. So we'll take an example in the hands-on session. So the tracing that you can do with Python, for instance, you can use OpenTelemetry for it. So in OpenTelemetry, apart from the core SDKs themselves, there is something called as the Cloud Trace Span Exporter. And when you bring this in, you create a brand new span, right? And that span is going to be used over the predict function, right? And as part of that, you send the latency and the context info. And because I use Cloud Trace Exporter, Cloud Trace is actually the Google Cloud's native service for tracing. All this information of tracing every single request will automatically come in, show up in the Cloud Trace dashboard. We'll see an example of this in the hands-on. And then you can get the trace ID and start incorporating that in the logs. That way, it's all correlatable back and forth. Okay. For ML models specifically, what else can you log functionally? One interesting set of things that you can log would be, the prediction confidence and even things like top K classes. So, especially useful for LLMs. So, what happens in a chat completion kind of a context or in a generation kind of a context is you're predicting the next token from amongst a set of candidate tokens, and the LLM decides or the network decides that one specific token is the most suitable because it's got the best score amongst all the other neighbors that have also been searched on. So when you want to debug something, it's very useful to just emit out all of those top K classes along with the prediction confidence so that you can log all of this and take a look at how the performance is across a set of candidate options available to you. Naturally, this is going to be super expensive if you do it for every single inference request, and the inference requests are very large. So for chat completions, as an example, every single word, if you're going to do that, then the tokens being, let's say, 1,000 or 10,000 for every request makes it balloon up in terms of cost. So therefore, you may not want to log for everything, every image or every input request for prediction. You might want to do it once in 10, once in 100, etc. The other thing that you can log is input anomalies. Like as and when you measure something is, drifting away from what you're expecting as a normal distribution, you start logging that information. And then log when the outputs deviate as well from what you are expecting to provide. So the example I gave earlier was, even though I'm changing the input data, the outputs the output class keeps getting predicted to be the same. So that's an interesting anomaly to log. So what happens in production is often that the model is running for some time, and then you get a complaint that the model is not performing the way that you're expecting it to perform. So in which case, what you cannot do is go and change all of those production code just for the sake of understanding what is happening. So you'll make do with what has already been instrumented, make do with the observability logs, and then see whether you can also do some couple of other things, right? One you could do is something called as a shadow deployment. So what you do here is the traffic that's going to the production machine learning system, you do not touch that. But because it's going through, let's say, a load balancer, you make a copy of that data, send it to your canary model. The canary model is not responding back to that um, request for prediction, but it's just logging that information and then giving uh, all that information for um, helping you take simple calls as to whether the main model is suffering from readiness issues or it's suffering from underlying resource issues, whereas the canary model is just running canary model is just running fine without any failures. So it helps you compare liveness, latency, as maybe that's the root cause, and that can be root cause quite easily if you follow this shadow deployment approach. Or you take a look at the input requested data and form patterns on top of it. And using those patterns, you can analyze and see whether that's actually causing the problem. The second approach is you start logging the requests themselves, right? By enabling a flag, right? For instance, you can have a debug logging in your code that's already there in production, and the debug logging logs the input data, the request data itself. But because of privacy concerns, you take care of sensitizing the data, or you log only once in 10 requests or once in 100 requests. And then when you've got to debug this entire thing in production, you enable debug level logging to be collected as well. So that way you get access to the actual raw logs without the sensitive information. And also the volume is not that high. Last but not the least is replay the logs in a test environment. Obviously, that's possible only if you log it in the first place, but then the inputs that you've logged, you can take that and put it into a test environment and replay it to see what the behavior of the system looks like. So that's how you would debug large ML systems in production. Great. So with that, we've come to a close on what we wanted to discuss about monitoring, performance optimization, right? And how we looked at the three pillars, right? Monitoring, observability, and response, and looked at ways in which you can use open source tools for getting your work done. In the next video, which is going to be the hands-on video, we'll take a look at the GCP native tools available to us, along with a couple of the open source tools, to make our own models be ready with the best practices for monitoring, logging, tracing, performance optimization, right? So that's our focus for the hands-on portion of this week's lectures. Thank you. I'll see you on that video.